giant draft science video, I think. Yeah, pretty much. Anyway, so I've been thinking about light some more, mostly in regard to this diffraction thing and what's actually happening and mechanics of that and blah blah blah. So it had me thinking about lots of different things, mainly about this idea of what moves a photon of light. What actually makes it change its direction. What's the game? So I thought I don't have an answer, but you just know what the answer isn't. So what I'm thinking is you know that, like, an example of a place where commonly we see this happen is with heat coming off the ground. When vapor's moving, and that vapor is a change in density. So it means the atmosphere is different densities. And I guess what I'm thinking is between densities, that it's essentially means that it's a dividing line between the regular atomic bonds, molecular bonds, let's say, and that's sort of what's created when there's a change in density. A change in density is it has a line to it. There's a reason there's a change in the density, right? There's a reason why the stuff bound in one blob isn't going to the lighter density in some instantaneous way. It takes it time to do that. It takes time for something in the more compacted density to be liberated, to take space up in the less compacted density, you could argue. And what I'm thinking is that there's an ion field between these densities. Anytime there's a structure, an end to something, the end of my fingers versus the air, but more particularly like glass or prisms, they have these surfaces, where there's this transition point, and that's where all the action is supposed to take place, pretty much. And so I'm thinking that's a place where there's always these ions, that the surface of everything is covered with them. And it's these ions is where the change in direction takes place. So I guess I would argue that light, that glass, for example, just transmits light. I mean, light doesn't go through the glass. It goes through the glass in a specific way, through a specific absorption, readmission kind of thing. It gets caught up in little wheels as it goes along, or it gets tunneled or funneled, or it gets angularly bent, and it's doing something going through. It's transmitting through glass. It doesn't go through passively. It doesn't just go through the empty spaces, so to speak. It doesn't go through unmolested. It's molested a lot. So it's transmitting light. It's moving light from one place to another place, obliging it to travel a path. Lots of ways to say this correctly, but anyway. But it's not really interacting. But at the surfaces, something happens. The surface between glass and the air, for example, you end up with this diffraction. So this is the background of I've been thinking on this kind of stuff and trying to figure out the non-wave way to explain why there's a difference, why there's a change depending on these surfaces. So that got me thinking about field lines again. So I guess let's play with that for a little bit. See if I got didn't take much of a note, but light transmitted through substances, heat breaks surface. No, it doesn't really do that. So that one I crossed out. That one I didn't cross it out, but I crossed it out now. Alright, so anyway, the idea is that everything has this EMF, an electromagnetic field. I think it's either electric or magnetic, but whatever, doesn't matter. You have a polarization. There's no like big things that are monopoles, meaning that they don't have a pole, that they're not polarized in some way. They have a positive side, a negative side. Inside's negative, outside's positive, back's negative, front's positive, something like that. So there's all kinds of that creates this idea of a field in terms of these field lines, like are traditionally, well, I draw some, around magnets or something. They're not really real things. They're just arbitrary places in time and space that, it just more has to do with just a mathematical thing. And what it has to do with is the relationship between say any substance. So you could look at a slit and you could think of it in field lines like this, or you could think of it as a bunch of radiation coming out, little lines, and that both poles would be radiating. And so what field lines sort of represent is where there's a neutrality between the two kinds of radiation. So if this was black radiation, this was white, or this was positive and this was negative, what you'd end up with is a place where, if you factored the two things together, intensity of their vector and the angle of their vector, they would create something parallel to what would be this line you would draw, this arbitrary line. And what happens is things tend to want to line up on those lines, line up on the lines they'll create. So like, say, with magnets and the little metal filings, what's really happening is there is no set lines that the magnets, that the filings will line up on. The lines are sort of dictated by how they're spaced. And so once the little pieces, once the filings start lining up, they end up being magnets themselves and oblige the next group of magnets to line up a certain way based on the fact that they start repelling each other and they start attracting each other, which means they either collect or they repel. So there ends up white space in between, because they either collect at one place or they repel at another place, and there's this proportional relationship that's going to exist. And so that's what's creating the proportional lines. So, but what's to understand in that, as I'm thinking about it, is that if you really theoretically thought about it, if, let's say, a bunch of ions would line up on those lines, like in the sense that when an ion, say an ion was out here, and the ion, just all I mean by ion is that you have a dipole. Okay, you have an unevenness in its pole. It has a negative side and a positive side that's dictated by the swinging of the odd electron. So the odd electron is creating an unevenness, a lack of proportionality, something like that. Anyway, it doesn't really matter, and so this thing would tend to line up with its, say if this was the field lines from a positive and a negative, it would tend to line up with whatever was proportional to its tendency. What's the right word to use? It would tend to gyroscope in a direction that was compatible with the energy coming off here. So the things pushing this way and the things pushing this way, right at the middle, would be dead even. And you can kind of understand that as you move, you would have an uneven push. One side would be pushing more, and that would change the angle. So this angle would be straight out this way, where this angle would be out this way. But it would be parallel to what are called those field lines. I'm still not getting that quite right. But anyway, the point is these ions would align their poles onto, let's say an ion was moving into one of these fields. As it moved into the field, it would start lining up and getting more and more perfectly lined up with the field. The field would keep exercising its influence on the thing to line up in that direction. So all I'm trying to explain is that it creates essentially what could be thought of as facets. So when there's really, and you can really think about this in the magnet sense. So when there's a magnet and there's a bunch of this, you have to draw the field lines correctly. Why do I want to make them all the way around? They go, well, it doesn't really matter, right? You'll get the idea no matter however I draw them. Yeah, and they come out the end here, and then they go around this side here. All right. Well, anyway, so so you can kind of think of this as your magnet, and these are what are the arbitrary. They could be any kind of spacing, but they're always going to be proportional depending on what's in them. But anyway, it doesn't matter. the point is as something comes into here, it starts lining up with it. And so when you would end up having essentially little magnets. So instead of thinking of it as a curved line, it's really a faceted line, because each thing, each ion that would say be falling or be in that position would be lining up on these facet lines. They would have their own facet lines. And so if you think of it as something with little surfaces instead of a smooth surface, you can sort of get the idea that each mirror, these would be like little mirrors, I would say, for light, let's say. And as light was coming into, say, a two-slit. So the idea of the two-slit is that you basically are converging the field lines. So the EMF, the static electricity, whatever you want to call it, the energy being radiated from these surfaces is changing the disposition of the ions in this atmosphere. And it's really hard to take ions out of an atmosphere. So that's another thing I was thinking about, was vacuums. Because as a vacuum is sort of dependent on there being an excess of pressure, an excess of molecular pressure. But ions really don't interact much, so they already can establish their spacing. And so like once you get to a certain point, their ions are far enough away from each other where there is no repulsing pressure. They're not producing enough energy to push each other away, or they're not shielding enough. It's like gravity, and as you get further and further away, it gets weaker and weaker and weaker, and there's a point where it's just not going to be significant based on all the other stuff that's going on. And so you can't really pull any more out. I mean, as you try to create a deeper vacuum, which means you just try to keep empty space for stuff to fly into, and then throw that stuff you caught out. I mean, that's how you basically create a vacuum, is you pull some stuff, you open a void, you open more space. And so as you make more space, like if I made more space in my house, then the junk would fly into the space, right? And so like you could just think of it as cleaning the junk out of my house by just keep opening a new closet that junk can go into. And I keep throwing junk into that closet, but eventually there's going to be a distribution of junk in here that's just not going to be all that interested in jumping into the empty space anymore. There's not going to be a huge amount of impetus to do it, and it would, I get you almost, it's like you can't create enough of a perfect empty space with enough time to do the pulling necessary. Let's say if you could create that empty space and it could stay that way for 10 minutes, and you could wait for something to fall in and then grab it, it's almost like you'd have to go fishing for the extra matter to pull out. So that's why this idea of a perfect vacuum is really difficult to create synthetically. But regardless, I don't want to get caught up in a whole conversation about vacuums. I guess it's only significant in the sense that we have to understand that the atmosphere is full of stuff. The stuff, okay, is going to align on these electrostatic fields that are created by the more substantive, by the matter. Matter creates these field lines, and these field lines will end up forcing ions to line up on them in a particular way, which means they'll be in particular positions, which means when light interacts with them, that light is likely to have a very definite incidence of refraction, or whatever you want to call it. It's going to angle off in a very specific way, depending on what it hits. And I guess what I'm arguing is that because these can be thought of as little facets, I guess I'm sort of, I don't, I have to draw this into a better scale. I mean a more visual scale. But you could argue that the angular difference between this incidence and then this reflection is going to create a probability of certain locations getting more hits and certain locations getting no hits. So I guess that's what I would say, that's where the proportionality exists, is in the fact that there'll be the very empty spaces that these that you would call the space, the angles not shown, or the angles neutralized by the facet. All the subtle little angles in that little curve you took out. It has lots of little subtle angles, and all converted into one angle. all of those little angles are end up being what you would think of as the dark lines. They're the things that'll never see a photon, because they'll never be at that angle, because it's always going to be an averaged angle. So in some sense it's like doing, when they do this two-slit wave math and the single-slit wave math, which I'll do real quickly just because it is kind of humorous. They're basically saying that, well, first they just arbitrarily say we're going to break the field into threes. Okay, for I don't know why they're arbitrarily allowed to do that, but they are. And then they say two waves are created at this 1/3 location. And then what they do is take 1/3 of that. So they break that into thirds. So they broke the original distance into a third. Then they break this distance into a third. And then they count only the angular difference between these two lines. So they're basically just taking these two and saying these two photons are the ones that are interfered with each other, because all the rest neutralized each other. That's sort of the argument. So only these two count. So they're almost saying that every location creates a wave, and they're only going to count these two locations. And what they're just basically doing is just taking, these two parallel lines. If you bring them to a straight line, would be the surface they're coming off of. So this is the opening of the slit, and what they're basically doing is just creating a right triangle, and then doing the sine thing, which is basically just taking the sine of this angle, which means it's just a relationship between this length of this line and the hypotenuse this line. So it's a proportion. So they end up with a number of a proportion, and that proportion will represent where they are in this artificially created sine wave. So 100% would be, let's just say this would be the 100% point, and then 90% would be some other place in the phase of the light. So once you create a proportion, you can just say yes, 1/3 or 5/8 or whatever proportion of that 100%. And so that's how they create the phase. That's how they represent the phase difference. And once they represent the phase difference, then they can just say how much destructive interference it is just by adding the two out-of-phase waves. So they just basically say the waves are this much out of phase. And so they say when you combine them, you either get constructive or destructive interference. So at this point you'd have pretty well, that's not a really good I should just use a wave that's completely opposite this wave, and then you can see I have to add more to it. But there you can see the destructive and constructive. So this would be complete constructive, and this would be complete destructive, in the sense that a peak and a trough would be a nothing, and a peak and a trough would be the maximum amount. A trough and a peak would be the zero amount. Anyway, so that what I have to do is figure out the angular thing of this facet thing, but I think that does account for how angles would be eliminated, and this would end up creating a kind of averaging. It would be averaged by the fact that the position of these ions, that are the things that are really bending light, are ions. Where you can have an irregular reflection, let's call it, where the light goes in one way and it'll come out some other way, where in regular matter it either absorbs it or transmits it, but it doesn't distort it. And then also you have the factor that these field lines would have different. So that this is another part of it that I have to figure out, that the field lines are arbitrary, but at different densities. Closer to the surface, the closer you get to the surface, the fewer facets you would essentially have, right? So you have fewer facets, so you have even more averaging close to the surface. So the close to the surface only has, like, you could say, 10 facets or whatever. Obviously it would have millions, but I'm just saying each one has proportionally more facets. So out here you have a lot more facets than you have here. and so there's a lot more averaging the closer you get to the material. So if this is one side of the slit, the more photons you can force to interact with this close to the surface where the facets will be the highest, the most averaging, and where you'll get the most likelihood of something comes in a little higher or a little lower, it'll just get averaged to one location. It'll get, the reflection will be out perpendicular to this surface, so it would end up just being averaged into a perpendicular response that would go in one location. So that's another way to look at this, is that as the density increases, as you force the light through a denser field of ions, the denser at the surface, they're also at the surface more rigid, more averaging in their angularity. So you can sort of understand, if I only had 3 ions, you could see that all you would have is 3 facets. So the light would have a lot fewer choices. So whether it came in here or it came in here, the fact is it would come out at the same angle on this side. So no matter what distance this was, this would get averaged into one location as an exit point. So, but yeah, obviously I have to convert sine theta, which is the ingredient in the quantum mechanic wave math, the sine theta, right? That's the funny little thing, whatever it is. But that's the thing they do that creates the proportional number. Okay, they convert the angle into a proportion, and it's the proportion that dictates the length difference in the wavelength, which decides whether you're got destructive or constructive interference at a certain location. And so all I'm doing is doing the same thing, except using your likelihood, the likelihood of a photon having 2 locations or 3 locations end up being 1 location in terms of where they're likely to be refracted to. Yeah, I think that sort of explains it. Yeah, I don't want to get into different wavelengths behaving differently, but that's I think you could sort of understand that depending on what kind of light's going in, there'll be a different change. There'll be a change in how the light would go out, because it'd be a different amount of time it would be absorbed by an ion. Let's say the ions have a certain rotation, and depending on where the light is going to be trapped by the ion, it would have a different orbit, let's say, and the size of that orbit, like ultraviolet light, might get trapped. Ultraviolet light might get trapped in an orbit here around an ion, and looped and released. And infrared might have a same, but it could be an internal, and so that internal takes less time, so it's released at a different angle. So they'd be released at different angles depending on how they come in, what wavelength they're at. But that's something to do, like I said, that I think the visible light spectrum and light, anyway, ultraviolet light to infrared light, the behavior of light and electrons, I think has to do with this pair relationship, where again, it's this, you have to hit it twice for the electron to be affected. And again, it's the electrons that are being affected. We'll just ignore this drawing. Ignore that. We just won't play with that right now. But I'm just trying to give an illustration of the fact that light isn't going through the atmosphere, or any substance we see it go through, glass, whatever. It doesn't go through unmolested. It's being molested. And the real trick is, it's molested in a diffractionary way by probably, I think, ions, or even free electrons, or even hydrogen nucleuses. Whatever's in the atmosphere that you can't get out of the atmosphere, that it's always in the atmosphere, and those things are just being, I would argue, also constantly emitted by objects. I mean, as an object has temperature, say there's a bunch of well, there's infrared radiation that's trapped inside of things as they heat up, but that infrared radiation doesn't really, not much of it escapes. But what does escape, I think, are these ions. So as there's a bunch of percolation going on, as your matter heats up, you don't see it, but you're probably boiling a little bit at the surface. You know, your surface is probably breaking pieces off all the time. So little pieces of you are flying off, but they're still statically or electrically attached. I mean, they're still, they don't escape gravity. So they basically move off your surface and then they're pulled back onto your surface. So there's a corona around you, an aura of little pieces of you that are being thrown off by the heat inside. The heat's creating a lot of movement. The movement's throwing little bits off of you. Some of the little bits are infrared radiation, but I think they're more likely to be little, more atomic style particles, bigger particles, like electrons and ions. And so there's a whole field of that stuff floating around you, and it's always being oriented to what you would, to the not the position of field lines, but to the orientation of the field lines. Again, the field lines are sort of arbitrary. The only thing that really matters about them is that they show the topography, so to speak, of where the neutral points are, between where there's a balance between the EMF, the other radiation. It really is another radiation. It's polarized gravity, I would argue, but it doesn't really matter what you call it. But that's what it's made out of. That's what electrical and magnetic radiation is really the two polarizations of gravity. And those affect ions in specific ways. Either being invisible to them. One polarization would be invisible to the ion, the other polarization would be opaque to the ion, that kind of thing. That's why one side is attractive, one side is repulsive. So anyway, is that all I wanted to get to? Yeah, so I don't have the math yet, but I think that's probably the nature of the math will be that the closer you get to the surface, the more averaging that will take place based on the incident of refraction. So a larger swath, a bigger clump of light coming in at different trajectories will leave at the same trajectory because of that faceting. Yeah, I think it's might be useful. So anyway, none of this is written on stone yet, but that's just me attempting to figure out a more rational explanation for light refraction and diffraction. Either one, both. Works for me. So like I said, all I really have to do is convert it into some sort of, I mean, all I'm going to really be doing is doing the same thing sine theta does. So I guess that's what that's the point I wanted to make, is that I think this will do exactly what sine theta does, which is basically I can just turn distance from the surface into a proportional relationship and just use those proportions to dictate how much distortion in angular momentum will be created. Well, how much distortion in angular direction will be created. And just say that the closer you are, the more likely there is to be a distortion based on averaging. Right. I think that's good enough. So, till next time. There is another angle to this, you know, actually just thought of it. So I'll say it real quick, just because it is sort of interesting. You know, because there's another thing I'm kind of curious about that I haven't figured out yet. But they call it, I don't know what they call this angle, right? This, whatever, it's 27 degrees, I think, where, you know, light will always reflect. All the light will reflect. So if you get to this certain angle, then everything down from here, all the light will reflect off glass. Every single photon will reflect. So once you get to a certain angle, every bit of light will reflect off the glass. So once I tilt a piece of glass up at a certain angle, it now has a hope of the light going through. But if I go anywhere below that angle, all the light reflects. And that's an interesting phenomenon, right? I mean, I find it interesting. So that might have something to do with this in the sense of these facets I was talking about. These facets would have either an ability to let light through, or it would reflect, which, you know, it might be relevant. I don't know, but it is it's something else for me to figure out. I haven't gotten to it yet. I had a theory on some of this stuff, so why go through it? You know, just because of this transmission thing, you know, and that you have this line between surfaces, you know, this space between surfaces where all this funkiness happens. And I was sort of thinking about it, you know, especially with density. The density would be like tubes, you know, and that like the light's traveling through a certain size tube. And when you change densities, you're changing the size of the tubes. And so what's basically happening is the light that comes in here ends up being shifted here because it goes through the center of the tubes. You know, and the light here ends up going through the center of this tube, and the light here ends up going through the center of this tube. So it spreads the light out. And so as your density changes, it has this effect of spreading and contracting light. And what can happen is that it can also do it in double positive ways. So if this had another density change, it could end up that this light would end up taking another scale up because it would hit one of these tubes, and then that tube would have another density change up. You know, so it could have a rather dramatic amount of change by just happenstance of it keeps positive. It keeps migrating from it keeps ending up in a tube that ends up being pushed up by the next tube. You know, kind of thing. So anyway, it's another way of looking at it, where it's just tying density to size of pipe, and then you can sort of understand that if that would be another averaging effect, right? Because you have 100 pipes going into 10 pipes, and the 10 pipes, it always goes down the middle of those 10 pipes. So obviously 90% of the light had to change in some respect. It either had to go down or up to fit in the middle of the other pipe. So its position was changed. So many things to fiddle with. So anyway, so it's just a concept video really, and more to work on. I just, you know, it is taxing on my brain. You know, having to go into the depth of this stuff, because all these things have, you know, there's just miles and miles and miles of stuff you can learn about just one single thing. You know, it's a little daunting. So anyway, until next time.